Hello! In this video, I'm going to talk about theorems. What is a theorem, and how do you derive one? So, take this sentence: if the sun explodes, then the sun explodes. Now, this sentence is a tautology, right? It's true no matter what. Whatever the state of the sun actually is, the conditional is true. If it explodes, then it explodes. And that means this is a tautology. And we're already familiar with the notion of a tautology from the truth table work we've been doing. You might wonder, though, well, can I derive derive a tautology in the derivation system? And if I could, what premises would I derive it from? Maybe I wouldn't derive it from any. After all, there's, when we derive an argument from premises, what we're basically saying is, well, if those premises are true, then the conclusion is true. But if a tautology is true, then it's true no matter what. So whatever premises you pick, it should be derivable. And in particular, if you pick no premises, it should be derivable, because you don't need any information about the way the world actually is to know that the sentence is true. And so, in fact, that's the case. We can derive tautologies from no premises. Any tautology, can you derive it? Yes. Do you need any premises? No. So that's what a theorem is. A theorem is the conclusion of a derivable argument that has no premises. That is, a theorem is a sentence that you can derive with no premises. So here's one simple example. Therefore, if P, then P. That sentence can be derived, or formula can be derived very quickly. You just would say, show the conclusion, and you'd say assume CD, and then CD. We'll see that in a second. As it happens, and it's actually not as it happens, it's no accident, the way we've set our derivation system up and the way truth tables work, every theorem is a tautology, and every tautology is a theorem. Right? We have these two notions, the notion of a tautology, that's a sentence that is true no matter what, and we have the notion of a theorem, that's a sentence that is derivable from no premises, and as it turns out, those two notions coincide exactly. Every sentence is either both a tautology and a theorem, or neither a tautology nor a theorem. So here are some theorems. If P, then P. If it's the case that if P, then Q, then if it's not the case that Q, then it's not the case that P. If it's the case that if P, then Q, then P, then P. That one's a real mouthful. Those numbers, by the way, T1, T13, T23, the derivations module in Logic 2010 numbers the theorems, and those are the numbers that they have. If you look in that program, you'll see at the end of the chapter 1 problems and the regular problems, not the 1.6 problems, just the 1 point whatever problems, or in the same with the chapter 2 problems, you'll see there are a bunch of problems that are just theorems, and they get these numbers in the program. Here are a bunch more theorems involving the conditional. These are pretty important theorems because they sort of they show how the conditional works in certain ways, and we will be looking at them in more detail later on. So let's just look at this one. If P, then not P. So this is a theorem. How would we establish that? Well, we would try to do a derivation of it without any premises. How could we do that? Well, we'd write on the first line, we'd say show if P, then not P. On the second line, we would do what we do whenever our conclusion is a conditional. We would make a conditional assumption. We'd say assume CD, and that gives us P. And now look, we can apply double negation. Say not P. Well, that's the consequent of line 1, so we can say 3CD. And there we go. No problem. Very simple little derivation, and that boxes and cancels. And so if P, then not P, that's a theorem. Very easy. That one is. Here's one that's a little bit longer. So this is the conditional. The consequent is R. The antecedent is a conjunction of P with if P, then Q, with if Q, then R. Well, so we do the same thing. We'd say assume CD, and we write down that big conjunction. What do you do with a conjunction? Well, you split it up, you separate the pieces, you simplify, so you get P. You simplify the right-hand side, which is a big conjunction, which you would then simplify again. And now we have if P, then Q, and so we can get Q with modus ponens with 3 and 5. And then we'll break off the right-hand side of line 4, giving us if Q, then R. We'll apply modus ponens again, giving us R. And now, look, we have the consequent of our show line, and so we'll apply CD. So there we can box and cancel this derivation as well. And that establishes that this sentence we've written on line 1, that sentence is a theorem. So the argument is valid. Therefore, P and if P then Q and if Q then R, only if R. It's a valid argument, and that sentence is true no matter what, and it's a theorem. And what we showed, or the first and the third, we showed that the argument is valid, and that means the sentence is a theorem. In fact, if you wanted to, you could take this sentence, put it in the truth table module, do an analysis of it, and it would come out to be true on every row as well. We haven't shown that. In more advanced logic classes, we would show that every tautology is a theorem, and every theorem is a tautology. But we're not going to do that in this class. That's just a fact that I'm telling you. What we are going to do is prove some theorems. What do theorems do? I mean, they don't actually give us new information about the world. Information about the world typically says, well, here's how the world is and here's how it's not. We rule in some scenarios and we rule out others. If we say he has, he has brown hair, then we say, well, there are all the ways the world could be. They're the ones where he exists and he doesn't, and then they're the ones where he has brown hair, and they're the ones where he doesn't. And we're in those ones where he exists and he has brown hair, and we're not in those other ones where he has black hair or no hair or doesn't exist at all. So that's a normal sentence. He has brown hair. It's not a theorem or a tautology, and it gives us information about the way the world actually is, because it says, well, here's the way the world isn't, partially. So theorems don't do that because they're true no matter how the world is, whereas the sentence is not true no matter how the world is. It's true only if the world is certain ways, and that's why it's informative. That he has brown hair, that's informative. It's true only if the world is certain ways but not others, and so that's what makes it informative. But theorems aren't informative like that. What they do is they're true because of the meanings of the logical words. It's true because of what and means, and the conditional means that this sentence here is a theorem, and if P then not P, that's always true, and that's because of the meanings of the arrow and the negation sign. And so when we state a theorem, what we're doing is we're showing how the logical words work. We're displaying their meaning. We're saying the meaning of this word makes this sentence true, so that's the kind of meaning that it has. And so if P then P, right, that's part of displaying how the conditional works. If the antecedent is true, then so is the consequent. Okay, so if you're going to derive a theorem, then you're going to need to use conditional derivation. We're going to learn another method of derivation towards the end of the course, and we'll see that we could use it to also derive theorems. There are theorems that we need that other derivation method called indirect derivation to derive, but right now the only methods we have are direct and conditional. Direct works only if you have premises, since when you're working on a theorem, you don't have any premises, and so you're going to have to use conditional derivation, as I did in the examples. So in your homework theorems, they're derivable because they're all conditionals. And so you get to assume the antecedent, and then it turns out that in those cases, you'll be able to reason to the consequent, and then you'll be able to apply CD once you get the consequent to box and cancel. So you're going to basically be producing these derivations in pretty much the same way that you have been before. You're going to need to make sure that you make an assumption, and it'll be assume CD, and then you're just going to skip the premise step because there are no premises to put in. You're just going to work with that assumption, and you're going to take the assumption and apply your inference rules and get to the consequent and then apply CD. So that's what you need to know to derive the homework problems that are theorems, and we've learned a little bit about what theorems are in this video. We will be learning more about their significance later in the class. So if you have any problems, any questions, please let me know.